Ready? Okay. I'm next Patel. I'm from National Institute for Computational Science and to present introduction to parallel programming techniques. Um, Thanks, Florence, for providing me useful slides. So here is the overview for today's presentation. First, I will start about basic parallel programming. Then after parallel concepts and terminology, we will include volume architecture and link taxonomy such as FOMC, MIMT, um, and so on. After talk mostly about architecture, shared memory machines, and distributed memory machines. And then after I will present software models like NCF and LCC and how you program this machine. And then I'm going to about how to design parallel programs. As you know, software has been traditionally written for serial computation. In the diagram, you have the problem and what computer it fits into the bunch of instructions set. And then it passes to the CPU to process it. But this whole process is serial. It fetches the instruction and passes it to the CPU. And so how the parallel computing works? So basically, in the parallel computing, you have the problem, and you use the multiple instructions, and multiple instructions. So you see like T1, T2, T3, T4. Those are the time, and at one particular given time, use the multiple instructions executing to the multiple CPUs. So that's the basic idea about parallel programming. So the important thing is like why parallel computing, right? And there are reasons why we need to use parallel computing. And most important are the time. So if you do the parallel computing, then you can finish your computational work much more speedily than the serial computing. Another to solve the large problem. So if the very big matrix computation, let's say 10 million by 10 million matrix, then you can use parallel computing and solve the problem. And another important thing is provide concurrency. So now, if you work on multiple problems, you can work on multiple problems at the same time and get the result. If using the computing. And results may include like taking the advantage of non-local resources. So let's say you have access to supercomputers, then okay, you can write your parallel program and use the supercomputer. Another cost saving. So it may possible you can connect the bunch of CPUs and create the cluster, and you use that cluster to solve your problem. And the most important thing I think nowadays is memory. So most of the CPUs, they have 8 gigabytes or 62 or 100 gigabytes of memory. But for some of the problems, that may not be enough. So you have to think like how I'm going to fit this huge data set into the memory. And using supercomputers, you can divide your data and fit into the multiple CPUs and solve the problem. of the limitations of serial computing. The actually this slide, I have to go to this next slide, that is the Moore's law. Why? How important it is to think about the number of transistors available on the chip and how increase the frequency for the core unit on the chip. So as you see in the graph, the first one, the number of transistors keeps increasing, and Moore's law says the number of transistors doubles approximately every 2 years, and the performance. But in the clock speed, it's already saturated from 3 to 4 gigahertz. So we cannot increase the clock speed, but we put more and more computers on chip. So because of the clock speed is saturated, the important thing is you need to think in terms of pattern, and then how to do the program. The another in the graph you see the performance per clock. It is also saturated, so it's not going to this further up, and the resistor. You get more and more transistors. You see the clock frequency. It's not going to increase anymore. So first limitation, like what physical and practical reason. The thing is the transmission speed. So as you know, we use the copper for the data transfer, and the theoretical limit for copper is 9 centimeters per nanosecond. So increase the speed, it's going to increase the proximity of the element. Another issue so the thing is we can use the number of transistors, but then we need to decrease the size of action. And another limitation is power and the cooling, because if we increase more and more transistors, it needs more and more power to run, and as well as more and more power to cool down. So here is just the information about what computing resources are available. So the first one is the physical computer, which multiprocessor, like your laptop or desktop. The next method with some specialized computer resources, like graphics processing unit. So nowadays we see like thousands of cores on the single GPU part. For the Intel many integrated cores, where it has 62 or 64 processing units and chip. And programmable gateway and specialized compute resources. And this individual unit, they are connected to the network. It may be connected to the Ethernet, it may be connected to some specialized, and or combination of above. So you may find some parallel computing resources, you may have the multiple processors, which is with NGR connected to Ethernet or specialized interconnect. Like, and so we have each node as 12 points, and then we are connected to the base interconnect. So how you are going to pose your problem. So basically, computational problems demonstrate the following characteristics. One is use a lot of data, and then you need to think how I can group the data into multiple chunks. Or you may have multiple tasks, and you think how I can divide this multiple tasks so that each task can be executed on different CPUs. So the future is parallel computing during the last past 5-10 years. That indicates the faster network distributed computing system and like hardware like the GPU or Intel Mac. let's talk about computers. How it works. After I will talk about plain taxonomy, which is based on this basic concept of instruction and data. As you see in the diagram, each compute processing unit has control unit, logic unit, and the memory unit. And some data into that, and you get some output from the processing. So here the basic design, where the memory and the CPU, you have the instructions and the data. So example is where B considered as data and that instruction. So what we want to do is that data. So and it processed in sequential. So it stores B, and then it performs the operation A plus B, and then it stores the results. All this have happened in sequential. So is based on this concept, instruction and data. And then after other two dimensions, the possible state could be single or multiple. Here, four different classes of system. Single instruction, single data, and called single instruction, multiple data. The multiple instruction, single data, and the fourth is multiple instruction, multiple data. We will talk about each of these one by one in coming session. So single instruction, single data. So what is a single instruction? That only one instruction is passing to the. It means you have only one value to operate on that, to work on that instruction. So for A, to load the data A, and then load the data B, and going to operate A plus B instruction, and then other computation and store the value of A. This is execution because it's going to execute serially. What is the expected output, and this is the most prevalent computing, like all CPUs and the desktop. It does this kind of thing, like it sends the instructions and the data, and it does the computation in serial. For single instruction, multiple data. So in like give an example of 3 plus B, and at that time A, B were scalar. Now let's assume A and B are now arrays. So A has values of 100 and B has value of 100. Multiple days, but I do the same operation plus. So I want to have the summation of all these values and to the third array that calls C. So data from 1 to 100. And so P1, P2, up to Pn, those are the processor to all and you do the instruction but on different data. Processor 1, it operates on element 1 of data array. Processor 2 operates on element 2 of A, and so on. So at one particular given time, all are executing the same instruction, low state. But that is, we are operating on the different value. This is operating on N, this is on 2, and this is on 1. So that's called the single instruction. The instruction remains the same, but you operate on the different data. multiple instructions, single data. So here concept is use the same data, but you may have different instructions. This is not the base example, but you can assume here you have function A, function B, and function C, different functions, but you are operating on the same value, A1, A1, and A1. So multi instructions, but the single data. And the last one in clean taxonomy is multiple instruction, multiple data. So if you see like processor 1, processor 2, and processor n, they have the different instruction sets. Like processor 1 has load A, load B, A multiply B, and so on. Processor 2 you call some function and does summation and calls some. It does some looping, call CI and do the looping, and it operates on different data. Like processor operates on A and B, processor operates on data set B, Y, Z, X, and so on. Processor operates on 1 to N, W, C, and so on. So multiple instructions, multiple data. Okay. SIMD and MIMD, those are the most widely used in parallel computing. If you look at here, the categories, one is the memory, another one is code segment, the processor, elements. So indeed, that the instruction multiple data sets only operates on distributed memory machine. In lesson, I will explain in more detail what I mean by distributed memory machine. And MIMD can operate on distributed and shared memory both. So the input remains same on processor. On MIMD, it may remain same or it may be different. As we see the last example, this is the MIMD where different processors have different instructions. It has a log step. So because all processor has to execute the same instruction at a given time period, so they has to wait until to go to the next step. Why the processor doesn't has to wait for another processor. And the it's a different for a processor because processor operates on value 1, processor 2 operates on value 2, and so on. And MIMD is the same thing, it can operate on different data. So SIMD is mostly the data parallel applications where you have a lot of data and you want to operate the same operation at particular time period. While in MIMD, it can be data parallel. So I have the data and I want to operate same instruction, or I have the multiple function and I want to run the multiple functions simultaneously. So yeah, parallel. SPD, that is called a single program multiple data. That is special case of multiple instruction multiple data. The last class of plain taxonomy. What happen in this SPMD? You have the program. And let's say you have one model and you have different files. You have the same model on these different files. So you run the program in such a way that each processor will read the different file, but they will same model on different files. So that is like you have this whole program and you have this multiple data and you want to run this in parallel. The approach is called single program multiple data. Look at the architecture, the parallel architecture. So it can be, this may not be the first, but the one called the shared memory architecture, the one is called distributed memory hybrid architecture which is the combination of shared memory and distributed memory. And I want to also mention the GPU memory model because it's different than shared memory and the distributed memory. Just here in the figure 4. So you may have the 4. So you may have your 4 to your here is 4. Generally, each core has a core L2 and L1 share. But so you cannot access this L1 and L2. But it can this and then main memory that we call RAM. So when I say the memory architecture, then I'm mostly going to talk about this main memory. Should have the most. So mostly this random access memory, the main memory, how it and how that way we can the parallel. So example of shared memory. The most laptop or desktop, because now most of them are. Oh, thank you. So the most common examples are Dell and laptop. So it has 4 CPUs, 4 processing units, but they share memory. It's called the global address space because it can be accessible by all these 4 CPUs. And then, like, if you store some value here, like a equal to 10, memory, this group can access that memory and it can change that value. And this group can also access that memory, so also access that variable and see that value. It may be possible that 2 CPU can access the memory and changing the value at the same time. Then you need to lock on that variable. So one CPU cannot change the value while so with further down means this shared memory is divided into 2 classes. One is called uniform memory access and the other one is called non-uniform memory access. So CPUs, they have the uniform memory access because the distance between the CPUs and memory are almost the same. So the to access the CPU memory is same as accessing this view this memory. That's called uniform memory. And in uniform memory access, there is this concept called coherent uniform memory access because if one processor updates the one variable, it automatically going to update the value in the global space. So whether if you can see that update. So that's why we call the cache coherent uniform memory. Memory access. As I mentioned, it may possible distance. It may not be the same. So in that, some takes more time to access the memory than others. And non-uniform memory. And make this concept called cache coherence because that way it maintains the consistent value across all the. This one machine at NIC called the which non-uniform memory access shared memory machine. So in theory, it is shared memory machine, but if you see physically, it's not. It doesn't look like it has 4 terabytes of memory. Each has the memory, but the way the interconnect setup, it can make this distributed memory into shared memory. So in your laptop, you see this memory and then 2 processors. In this Nautilus, is a different processor and different memory, but because of the interconnect, you can when you run the program, you can treat as a memory machine. Okay, so your shared memory. So one of these, you worry about um, sharing, so like it's all shared. So all this I have access. So if they say I want to share this variable to someone, or it's already all shared. So any CPU can see that value. The disadvantage of this architecture is less scalability. So see the computer with 100 cores, it's not practical. Once you increase the number of CPUs on the chip, uh, you design your memory so that way each processor can access it. And that's the real disadvantage of the shared memory. You cannot you cannot scale, you cannot do that architecture. Yeah, and as I mentioned, like if multiple CPUs are accessing the same data, that's responsibility to put the lock on that data. Otherwise, each you will see the different value for one particular variable. So that's responsibility to put the lock mechanism, so that way all CPU will have the consistent view of the value. And yeah, the expense it is also to design the large time memory machine comparatively designing the large distribution memory. So here distributed machine and how it looks. So you can consider the CPU memory block as your laptop or desktop. So here I hold desktop and laptop. And I connected them to the network. These interconnect or specialized interconnect, like interconnect, SPI interconnect, or IP interconnect. So as you see, like if you are running the program here, and if you have some array like ENP, it is stored here. So those processes or tasks are running on this CPU. You can access to this memory, and you have to use some message passing library. So then you can pass the message here and say, I want the data of 8 years or I want data of 3 years. The one of them, the example is MPI, that is for the message passing library. That is a de facto standard for programming the distributed memory. So in the standard, there are many implementations that are available, like OpenMPI, PMPI, SPMPI, Intel MPI, and so on. That's the standard to program. So the advantage of distributed memory. So this machine is up to thousands of cores. The example is that. So we have about 108,000 or 110,000 on that machine, and so each processor has its own memory. So if you are doing the operation locally, then you have to faster access. You can see here, if I'm doing some computation here, and if the data is located here, then it's easy for this to get access, right? So what the one of the disadvantage or one of the hard things about it is the programmer is responsible for data communication. So if you have some data here, programmer is responsible to program the way that this is and the data here. And non-uniform depend the distance, how far your data is from different takes different times. The comparison of disk memory machine along with uniform memory access of shared memory machine and non-uniform access of shared machine. So example of that symmetric and the old machine and the access machine like SPR and power 4 and the memory machine like and IBM as well. So you can use like shared form, shared non-uniform, or distributed. You can use NPI interface to program that. Thread, OpenMP or shared memory tools you can use on shared memory. You can use thread on distributed memory until unless you are doing hybrid programming where you have the NPI and after within the node you do some computation using thread or OpenMP. But without that, it's not possible to use threads or OpenMP to do communication between the nodes. You have to have a message passing library, like or one of the EBM or some socket libraries. Okay.
And so NPI in many cases
Right.
in Germany, you do the same?
Yes, you still have multiple.
Yeah.
Yes.
You're saying about
Right, right, doesn't matter. Yes. Means in implementation, what if they figure it out, it's a sharing machine, then it makes some smart decisions. So rather than the individual data, shares the data in the way that it doesn't have to do the communication like sending the data and receiving the data because it's already shared. And here distributed shared memory where each node has like multiple CPUs. Like as I mentioned, has 12 cores for node. So here is the 12 CPUs and memory, 12 CPUs and memory, 12 CPUs and memory, 12 CPUs and memory. And they are connected to the network. So how do you do it's conquered advantages or disadvantages to channel. So idea about this like if you work. So here is the simple diagram about how the CPU and GPU are connected and how it works. So CPU and here is the main memory. So that's you can set the text for example, right? You have CPUs and you have memory. And here is CPU. There is a NVIDIA G4 for example. use GPU for computational purpose, let's say, for example, mathematics. What you do, first, you copy data to the GPU memory. So you matrix A and matrix B to memory. And then after you send the instruction, which is the multiplication. So in the instruction here, the GPU executes the instruction, do the computation, and after it copies the result back to the CPU. Because you cannot direct the CPU, and that's why copy the result back to the main memory. So you can see the GPU memory model. So if we have visited the CPU memory model, where it has L1 cache, L2 cache, L3 cache, and the main memory, which is RAM. Here is the port that is the main CPU memory. This is inside the host, and this is the rest, which is the GPU. So you are to if to the main memory and access the over memory, constant memory, section memory, and the GPU has CPU inside, and each CPU has the register memory, each CPU has the local memory, and those CPUs are divided into the blocks. Like, for example, your GPU has 64 blocks, and so divided into each block. So that is block has been processing with the block. So those units have the shared memory, but cannot access this shared memory, and that's what the global memory. So when I'm done some computation, it stores the value in the global memory. So we can access this GPU, the multi-level system, like local memory, global memory, constant memory, texture memory, and so on. So we have talked about modules like parallel and how they are connected and how they work. Now about in terms of programming. So different types of programming models like shared dictionary model, tree model, the model, task model. So let's one by one. So as I mentioned, like the software, right? So this model exists as an abstraction about our hardware or the memory. And what important thing I want to mention here is there is no thing called this is the base model for this architecture. You can apply any model to any architecture, but in case you need to think which may be the better suitable for the architecture. So I want to run my code on Kraken, then I need to think, okay, is it going to be helpful for me to use NPI? Can I use some other model to use the Kraken? So this, of course, there is a bad model, but there is not a equal like this is the best suitable thing for this. Model. So as you know, I use the that it has global space and processor can access the data. So shared memory model, and in that you need to apply the law or transfer to close the variables. The one advantage of this one is it's globally stored, so that there is no sort of data locality, and that because of that you may see some performance issue because some persons takes more time to access the data than others in non-uniform memory access. So, and so for that abnormal model trading. So as you see image, there is one subroutine, two subroutine three, and subroutine four. So here is program which is subroutine one, two, three, and four. So I'm executing one process, but it just has four threads, and those threads are in the space double. Okay. So here the four threads. So here are the four threads. So calling the routine one, thread two, calling the subroutine two, calling the subroutine three, and thread four, calling the subroutine four, and all the executing. So so each thread has the local data, and they get the entire resource. I'm not sure whether you are aware of threads or not, but mostly the threads are associated with the shared memory architecture and the operating system. So different vendor may have the different implementation of threading library. And there is a standard exists called the pthread. But some vendors they provide their own thread. So is associated with operating system implementation. So that Windows have different implementation of threads than the Linux level. For the model implementation, there are two popular libraries that exist. One is called PostGIS, we call it PostGIS, and the other is called OpenMP. And PostGIS is only available for C language, but if you use another language such as Fortran, there are wrappers available, so you can use the wrappers and call the library. And the open is the compiler-based directives. And show you the example how you can use the OpenMP. But this one is use internally. You need to put some pragma into your code, and that way you can use the shared memory architecture. Microsoft has its own implementation of pthread as well as OpenMP. So now let's talk about the model. So in the model, generally task has its own local memory, and when they exchange, they have to communication and the data to one node and receive the data from another. So this is explicitly because those data are not shared, And and those operations generally are the cooperative operations. So when you send something, processor has to do the receiving job. It's not going to come. Here is the example like we have divided to the multi-term. So owns the part of it, and whenever you do some type of operation, they will to read that data. And you can also on share memory machine. So here like this already which is memory machine. So all can access it. The thing discussed so far is like shared memory model and the distributed memory model. On shared memory, you have the component P and in the distributed memory MPM. Parallelism is it that it in terms of the concept like the concept is it doesn't have any association with the libraries or tools. When I say system, that means I have a lot of data and I have the same task that I want to operate on, and that's the data parallel. It's like when you have the loops. Loop is the great example of data parallelism. You want to do the same thing because in the you define this code, the segment, but you say I equal to 0 to something or I equal to 1 to n. So that thing like indexing it says the data, and the second segment or the part of or the body of the loop is the same stuff. In the example, the dense linear algebra operations, matrix multiplication, eigenvalue, or choice factorization, those kind of operations. Those are perfect candidates for data parallelism. So, the example of data parallelism. So, I want to do the multiplication. As you see how A, J, and I indexes. Starting from here is my body, right? CO equals so how can convert this sequential code into parallel code? So you can see it's really easy. You see what I have added into that code is OMP parallel to the end parallel to, right? I run this code on shared memory machine. So now with 16 code, but it can automatically identify how many codes are available on the system, and then it can spawn that many threads. And this code on 6 so this is all of data parallelism. Okay, so we want the state, right? And here I found state needs to be spawned, but OP library can by default identify how many processes available on the system. So if you want to run a laptop and it has 4 cores, it's going to run this part. Sorry, yes, individual dependent. But the thing here is if you have the dependency here, then it will if it's data dependent, let's say the previous operation is dependent on the previous session's value, then you cannot do the operation in fact. But when you have the data independent operation, you can have it. So now we talk about the task parallelism. So what what you have is you have different tasks. Let's say you have function A, function B, function C, function D, and you want this function in parallel. Other that they are not dependent on each other, right? And so this task parallelism is called force parallelism because it's the function works straight into the task. So it has sometimes it's easier to implement and has the less overhead than the data parallelism because data parallelism you have already on the data and that those data of course are those are important but they are in the shared memory space then you may need to pay the penalty for accessing the data. In here operating on the same data but different data. So now parallelism where you have A, B, and D. These are it may be possible different tasks take different time. And let's example. So here the original code is serial code, and you have code segment A, B, C, and D, right? And if you in you just open OpenMP section code. So as you say OpenMP parallel and it's OpenMP end parallel. That means this thing are to be executed in parallel. And I define OpenMP section and section. That means I have 4 sections and I have to run all these sections in parallel. So I want to mention one about OpenMP. So this parallelism can be done. That means in instead loop, what you can you have to the output and say okay, then parallelize this output, and then you make and then the performance improve and then the inner loop is also independent. The on top of it that way you have the 2 loops in parallel. So you need the loops in parallel. If you have multiple sections, you can just run 2 sections in parallel and see how much performance difference it makes. If you have function or multiple calls with different functions, you can put parallel section on top of those things and those in parallel. I think, and there's the type of exists like the high where parallelism as well as task parallelism. You have the individual features. You have and the GPU includes like CUDA. So good combination of all these different libraries and or some other tools like we also have this tool called Swift, which is useful to do the to program the mind. This tool because we already discussed about SPMD and MIMD. So let's talk design of the program. How this program parallel program. So here I have a lot of in my agenda. Let's see how I about it. If possible, I will skip some of these topics. But like what is this manual parallelization? So looking with the manual parallelization is time consuming. If you have enough time and if you wish to learn about parallel programming, then parallelization is useful. But if you just want to get some results, then you can do the automatic parallelization. Then you can use some flags in your compiler and this the compiler are smart. So if they identify the groups and those groups are not doesn't have dependencies, data dependencies within the loop, then it automatically parallelize those groups. Fortran compiler is a great example of this. If you have the Fortran code and it has a loop inside it, it can automatically those groups or parallelize those groups. The another thing is programmer type. So using the OpenMP data set, like as you see, I just put the OpenMP file, do or action, and it's parallelized as part of. So that's an easy way to do program on parallel architecture. So here is one thing about which code can you parallelize and which code cannot be parallelized. So let's take an example of highlight the potential energy for several of independent conformation of a molecule. And when done, I have to find the minimum energy conformation, right? So you here potential energy for just areas out of independent conformation. So those are independent. That means I can calculate those in parallel, right? And result, I can do the finding of minimum energy. So when I have got thousands of data, I have a parallel sorting algorithm in such a way that it can run on multiple cities. Can be done. Now, problems like I want to calculate the Fibonacci series. So this time is hard to parallel because each question is dependent on the previous one. It doesn't matter how deep I have, how large this system I have. It will parallelize this program and run on. Okay. So find some code segment which can be run on two different machines, like if you are running from connecting from and internet, try to find kind of things in your program. Another thing you can use the profile, which gives information about how much time spent in each different operation. And like, so if it takes too much time in this particular code, or from the line number 25 to 50, then I should think about making it better. And identify it takes a lot of time, right? It's complicated. So then you need how I can implement parallel reading and writing, so that way it takes less time for reading and writing. I mentioned, but you need to think about whether it's dependent or it takes time. If that is make a program better. So I think this is the interesting thing I want to talk about is the partition, how you partition the data. So there are most common ways one for the function decomposition. What you have, like your problem data set, you divide the data set, run on different using the different tasks. Now, partition the data in different ways, right? I have the one block where I can partition um, in the vertical manner or in the horizontal manner or in the cyclic fashion, right? And this is really important when you really care about the memory access, how your is accessing the memory, because sometimes it may possible if we are not stored in proper way, then it takes a lot of time in the data. But if you just change the storage format, then it can give you the huge performance improvement. And the cyclic format reminds me this implementation called the ScalaFest, that is the scalable linear algebra library. Does the cyclic memory format, so that stores the information, and now they have figured it out. This is the most important store that data. Decomposition. So you have the problem instruction set rather than the data. And you divide your instruction in such a way that that one is executing on that part and also on part and so on. And the thing I want to talk is the communication. Figure out whether you should do the communication or not, right? If the data are not dependent, then you don't need to do the communication. But if they are dependent, then you have to do the communication, send the data to another node, receive the data from another node. And just to concentrate the communication, time it takes to do the communication. That's to consider. Latency versus bandwidth. So how much time it takes to send the data from A, and how much amount of data you can communicate in the unit of time. Available to, rather than handling the small data like 1 KB, it's available to and handling rather than 1 KB of 100 messages, just send the one message of 100 kilobytes. Synchronous communication. In the synchronous communication, after certain calculation, you have to go to get the answer process. But if asynchronous communication and your problem is too stable, they don't have to wait, and that way it can fit in bit faster than synchronous communication. Because in asynchronous communication, it doesn't depend on the process to receive the data. And here is how broadcast the data and how you collect the data. So this is communication where you have the data and you want to broadcast to all with you, or you want to scatter to the different. So a helpful example, and then I have the profile there, and how this is all the so how function call another function and so on. So and then I can figure out how much complex it is and how much over it has for the communication and reading or writing the data. So this is only the partial list. There are many other factors for the communication and writing the parallel program. So what you need to do when you want the data dependency or load balancing or IoT. But I'm not going about this. But you will have these slides available, so you can look at slides and or contact any